Hi, I'm Ashley Tyson. This is my lab 5 about a falling slinky. The purpose of this project was to determine how well a simple physics model can predict the motion at the top of a falling slinky. My hypothesis was that the top of the slinky would follow free fall motion under gravity, meaning its position would follow the equation y equals y naught minus 1 half GT squared. I also expected that the bottom of the slinky would remain nearly stationary for a short time due to the internal tension forces within the spring. In this experiment, the system is a slinky, specifically the top of the slinky that I tracked. The surroundings include the Earth, which provides gravity, and the air. The main force acting on the system is the gravitational force pulling downward. Air resistance is present but small and was neglected in the model. There are also internal spring forces within the slinky, but these were not included in the simplified model. To model the motion, I use GlowScript to simulate the behavior of the slinky. The code updates the position of the top of the slinky over time using the free fall equation. At each time step, the position is recalculated based on constant gravitational acceleration. This allows the simulation to represent how the slinky would move if it behaved like a simple object under gravity. In my model, the top of the slinky is treated as a point mass undergoing free fall. The motion is described by the equation y equals y initial minus 1 half gt squared, which goes over kinematics and Newton's second law. This assumes that gravity is the only force acting on the system. The model also assumes no air resistance and ignores the internal spring forces of the slinky. The model predicts that the top of the slinky follows free fall motion under constant acceleration due to gravity. When compared to the experimental data, the overall downward motion shows a similar trend, which supports the idea that gravity is the dominant force acting on the top of the slinky after release. However, there are clear differences between the model and the real motion. The slinky does not behave like a single rigid object. Instead, it is an extended system with internal tension forces that affect how motion travels through it. This is why the bottom of the slinky remains temporarily stationary, which is not captured by the simplified model. There are several sources of error that may explain the differences between the model and real motion. First, air resistance was ignored, and second, measurement uncertainties from video analysis may lead to difficulty determining position due to camera angle, resolution, or frame.